operation. As I highlighted last time, this is a very important practical topic. You need to be familiar with it so you can make the right choice when you are doing encryption of a large message. So what was the idea? Why do we need this? Anybody can remind us? What's the context of this discussion? When these modes of operation come to the picture, when do we need it? Thank you. When we have a long message and we want to encrypt that long message, we have to divide it into blocks, and the size of those blocks is decided. How do we decide the size of the block? No, not based on the key. It is based on the algorithm we use. So each algorithm has a fixed size that it works with. For example, DAS, what is the size? 64, and AES, 128. The key could be 256, but the block for AES, the key could be even 256, but the block with which the algorithm works is 128. So we go ahead and break down the long message into blocks, and then we have multiple ways of going about and doing the encryption of the whole message. And these ways, now hopefully you can make sense of this diagram here. These are the two major categories of modes of operation. The first mode is deterministic mode. What do we mean by deterministic? What is deterministic in this context? What's the opposite of deterministic? Probabilistic, okay. So, for example, we see in the first method, the naive method, the first thing that comes to mind, the electronic codebook mode. This electronic codebook mode is a deterministic mode. Why is it deterministic, and what do we mean by deterministic?
One-to-one relations.
One-to-one relation between what? Between what and what?
When we encrypt the plain text, we get the same cipher text. If we encrypt it twice, we get the same cipher.
Okay, very good, yes. So basically deterministic means for a particular plain text message, we always produce the same ciphertext. We always, like if we do one message, we encrypt it, and then later on we encrypt the same message, we get the same ciphertext. This is called deterministic. In fact, you could start doing, for example, this block will correspond to the cipher. You can do one-to-one mapping between the plain text block and the ciphertext blocks. For example, if you have the block says Qatar University, this block will always have the same cipher. That's why we call it electronic code book. Electronic code book is kind of an old name for a lookup table. You have a lookup table. You can think of it as a hash or a dictionary, and basically you can look up. Imagine this huge table. You can look up any plain text. You get the corresponding ciphertext. It's one-to-one mapping, and this mapping does not change. You do it 10,000 times, same message gives you the same ciphertext. In the case, or the ideal aim of cryptography, you give it some text. It should really give you something random, really random. You cannot link it with any plain text. So in this case, in electronic codebook, we are able to link the plain text with the associated ciphertext. So, and this could be subject to a substitution attack. Somebody can watch our channel and learn the mapping between the plain text and the ciphertext, and then they can do substitution. And we've seen the example of this attacker trying, capturing the traffic from two banks, and they transfer a couple of transfers they do themselves. They learn the encryption of their account, and then they intercept other messages, other transfer messages, and then they replace other people's destination account with their account, as an example. So To summarize, deterministic is one-to-one mapping between the plain text and the ciphertext. If we have this scenario, then we can be subject to substitution attacks. Although this mode has an advantage of, what is the main advantage of this mode? Simplicity, and more importantly, faster. Why is it faster? Yes, because you can do it in parallel, because there is no dependency. If you remember, each block is encrypted and decrypted independent of the other block. So it can be super fast, but this is the disadvantage. Disadvantage is it could be subject to substitution attacks. Now, to remedy this, people invented other modes, which are not deterministic. On the other hand, they are probabilistic. And the first cipher that we've seen that is a probabilistic mode of operation, or not a cipher. By the way, the cipher like AES or DAS is deterministic. It always will give you the same output. If you give it a block, of course it should give you the same output. But in here we're talking about a large message, not one block, a large message made up of many blocks. The encryption of the whole message should be different, even if you feed it the same text. That's the idea of modes of operation. Okay, so then we started looking at the Cipher Block Chaining mode. And this one, we came up with this one ourselves. If you remember, we managed to do it without looking even at the formal definition. So what was the basic idea of the chain of CBC, chained block cipher mode? Very good. So if I want to encrypt block P2, plain text 2, what I do, I grab the ciphertext of the previous block, grab the ciphertext of the previous blocks, XOR it with the current block, and then go ahead with the encryption. And I keep doing this. What I'm doing now, I'm chaining the blocks together. So this will be fed. If I want to do P3, I will first XOR it with C2 and then do the encryption. Of course, the key comes in as an input to the encryption. And I keep doing this. So this is visually how it looks like. Now, we can also express this one as equation if we wish. Now, what about the first block? What do we do? So we XOR it with a random block that is randomly generated. We XOR it with called the initialization vector. And because this IV is random, the whole mode of operation becomes deterministic or probabilistic. It becomes probabilistic. Why it becomes probabilistic? Because we have one random input. The whole message now, whenever I may feed it the same text, the same long plain text, it will always give me a different cipher because of the idea of the IV, the initialization vector. So what is the initialization vector?
Random.
It's a random number generated randomly. And what is the size of this IV? Same size as the block. In DAS, what will be the size? 64. In AES, 128. And it is random. And it is also a nonce. It should be used only once. We use it once, we never use it again. That's basically the idea. So here is how this is what I just explained. So you get a better security, you are protected against substitution attacks because even with the same plain text, you get different cipher every time, thanks to this random IV. So what are the disadvantages of this mode? It has to be sequential. You cannot do it in parallel because there is dependency. Before you can encrypt block plain text P2, you have to first encrypt P1, plain text P1, first block, because the output of the first block will be fed and XORed with the second block before you do the encryption. Yeah, so you lose that parallelism, which means it's slower compared to ECB. Also, if there is any change in one of the blocks, let's say this is a file, I encrypted the whole file, and there was a change in one block, you have to encrypt that block and the remainder of the file. This is another inconvenience. But we will see there are better modes, but this is one of the initial modes that was kind of suggested to avoid the substitution attacks. So this is the visual representation of this mode, and this is the algebraic equation representation. It's straightforward. What I do here, I take for the first plain text block, I XOR it with the IV, and then do the encryption using the key. The encryption could be DAS, AES, any other algorithm, block cipher algorithm. Remember, this discussion only applies for block ciphers, not for stream ciphers. Now, for subsequent blocks, from 2 to n, the number of blocks, what I do, I take the plain text of the block I want to encrypt, XOR it with the cipher of the previous block. This is what I-1 says, and then do the encryption. So straightforward. And by using this IV, which is a non-secret nonce, very important to highlight here. This is a non-secret. Even if the attacker have it, in fact, you send it in plain text to the recipient. Even if the attacker has it, they cannot decrypt because they need the key. The only way to decrypt the message is using the key. And it is a nonce. You will hear this term often in cryptography. Nonce, it stands for a number used only once. Number used only once. And because of this IV, the whole CBC is a probabilistic operation mode. It's not a deterministic, it is a probabilistic one. So this is the first idea of making it a probabilistic. Probabilistic means really the output of the cipher of the encryption looks random. You cannot learn any mapping between the plain text and the ciphertext. Okay, so that's one way of doing it. The other ways, there are other ways of doing it. And all other ways, what they do, they are called stream mode of operation. I will explain each of them straightforward. This topic might seem a bit complicated, but if you focus and go through it, it's simple. Okay. And all what is needed from you is to really understand each mode. So when you go ahead and do encryption in real world, and the API or the tool asks you to choose which mode you want, you make an informed choice. You understand what you're doing. Okay. So the idea of this other family of modes of operation is that they use the block cipher as a stream cipher. Okay, let's see what this really means. Let's first remind ourselves what is a stream cipher and how does it work. Sorry? Okay, it encrypts one bit at a time, or some of them they encrypt one byte at a time, like RC4 if you remember. And what's the key idea? What is at the heart of the stream cipher? The key stream generator. The key stream generator. So basically what you do, let's say bits coming in. As they arrive, you generate a random bit and you do XOR, and that's your encryption. You encrypt using very simple operation, XOR. You XOR your plain text with the key stream generator, with the key stream. And the key stream get generated using what? Key stream generator. What is at the heart of the key stream generator? Random number generator. And of course, you have to have the same key stream generator on both sides, otherwise you cannot decrypt. We have seen this, yes? Now, the idea here, we are using the block cipher. What do we mean by block cipher? Give me an example. DAS or AES. We are not using it for encryption in these modes. We are using it to do what? We're using the encryption algorithm as, thank you very much, as a key stream generator. And then the algorithm will generate for us a key stream, a random key stream. What do we do with it? We XOR it with the plain text to create the ciphertext. Confusing enough? Yes? So in these modes, what are we doing with the block cipher? Are we using the block cipher to encrypt? No. What are we using the block cipher for? To generate a key stream. Once we generate this key stream, what do we do with it? We XOR it with the plain text to produce the ciphertext. And there are many ways of doing it. By the way, these modes are the most common modes. There are other modes out there. But we just focus on these commonly used ones. So let me now start with this one. This one is quite simple. The output feedback mode. The output feedback mode. OFB. Okay, so let's see how it looks. This diagram might seem complicated, but once you take a close look, it's very simple, super simple. We are familiar with this concept of IV, yes, initialization vector. What it is? What is it? Random number. What's the size of it? The same size of the block we're trying to encrypt. Yeah. Now, what we do, we use our block cipher. Let's say DAS or AES, the first time for the first block, what we do for the first block, we take this IV, we take it through the encryption. We encrypt this initialization vector using the key. Of course, the key is always there. Then it produces for us what this will produce. A key stream, a random number. So we take a random number, we encrypt it using the key. It gives us what? An encrypted random number. What do we do with this encrypted random number? We XOR it with the plain text to produce the ciphertext. Now this is for the first block, P1. What about for P2, P3, and so on to Pn? What we will do? Are we going to generate an IV for each one? So how we will generate a key stream for the next block? Yes, we use, you see here, if I am in P2, I use the key stream I generated for P1, I feed it back to the encryption, to the block cipher, to generate another key, another element of the key stream, and I use it to do the XOR. So, for example, if I am in if I want to encrypt P2, yeah. So I will take the P1. Sorry, I will take S1 that was generated previously, take it through the encryption using the key, generate a ciphertext, and then XOR it with the plain text to produce the ciphertext. So what I'm using the block cipher here for? To generate the key stream. This block cipher in this mode, I am not using it for encryption, I am using it for generating the key stream. Yeah? And then the encryption and decryption, what the encryption and decryption is using? A simple XOR operation. What do we call this mode? Output feedback mode. Output means I am for each block I am outputting a key stream, a key element. Key stream means a set of keys. For each block it has its own key. So this is the output. And why do we call it feedback? Because we have this arrow going back again. It's a kind of a loop, a recursive loop. So first block the first block, I will use an IV, which is a random number, bring it in, take it through the confusion and diffusion using the key, generate a key stream, one element of the key stream. In this case, the key stream is not a zeros and ones. The key stream is a whole block. So, for example, the first time, S1, in DAS, S1, what's the size of S1 will be? It will be 64 bits. So I'm not generating a key stream 1 byte at a time, like in, let's say, in A5/2 algorithm that is A5/1 that we've seen that it is used by mobile phones, if you remember. Those ciphers are bit level ciphers. In here, we're using a stream cipher, but in each iteration, I am generating a block, which is basically, you can think of it as a key. This key has the same size as the block I'm trying to encrypt. Is clear? No? Okay, so let me give it another go. Very simple. The first, remember, we want to, let me go back, start the story from the beginning. What are we trying to do? We're trying to encrypt a large message, yes? And this message is made up of many blocks. So one naive way to do it, first thing that will come to our mind, how to do it, we take the message, chop it into blocks, and then encrypt each block separately, independent of the other one. Yeah? This will produce for us the ciphertext of the whole message. No problem whatsoever. But this naive way of doing it is deterministic, which means if we have messages that are exactly the same, you get the same cipher. And this is not good because it opens the door for substitution attacks. Now, people try to invent better ways of doing encrypting a long message by using a probabilistic mode of operation, not deterministic mode of operation. Now, there isn't only one way. There are many ways. That's why we call them modes of operation. One of them is CBC, we just looked at. Another way of doing it, completely different. It's not intuitive. It doesn't come to your mind immediately. But this, you need to look carefully and use your smartness and to come up with this idea. Yeah? So here, the block cipher, I changed its purpose. What the block cipher was initially, what is the purpose of it initially? The purpose of the block cipher, why people invented DAS, is to do what? Is to do the actual encryption. Is to take the plain text, go through the diffusion and confusion, multiple iterations, remember, and then produce the ciphertext. That was the original intent. Now people came after and say, oh, we don't want to do that. We want to use it in a different way. What's another way of using the block cipher? We use it to generate a random number, which means we can use it to generate a key stream. So instead of using the block cipher for encryption, we are using the block cipher as a random number generator. And by the way, DAS or AES could be used as a random number generator. And this is the evidence. Okay? So, taking this idea, so the basic idea we are using the block cipher as a stream cipher, as a key stream generator for a stream cipher. We know the stream cipher, the encryption and decryption is super easy. What do we do for encryption and decryption? XOR. What is the challenge in the stream ciphers? Generating the key stream. In here, the idea is to use the block cipher as a key stream generator. We all now clear on this idea? Now, how we do it? How we do this? This is an abstract idea. We use the block cipher as a key stream generator. But how we do it actually in practice? So one way to do it is, for the first block, I need to generate a key stream or a key to encrypt the first block. Remember, I chopped my long message into blocks. Now the first block, how do I go ahead with generating a key for it? I generate a random number, which I call IV, initialization vector. This is the initial random number. And what do I do with this IV? Generate a key from it. Yeah? Key string is basically a set of keys. So for each block, it will have its own key. How do I generate a key for each block? Initially, the first block, the lucky first block, I will get for them an IV. Then what do I do with this IV? Feed it to the block cipher, feed the key. It's like encrypting the IV. So the first thing, I encrypt the IV, and then this will produce for me what? A ciphered IV. Yeah, it's an encrypted IV. Then what do I do with this encrypted IV? I XOR it with the plain text to produce the cipher text. Now we are clear on the first block. What about the second block? So I use the previous key I generated, the key I generated for block 1, and use it as an input for the block ciphering, for the block encryption, block cipher. I use it as an input, use my key, use the previous key for the first block, encrypt it again using the key, and then it produces for me another key. I will call it S2. What do I do with this S2? XOR it with the block 2, and this will produce the cipher text for block 2. Block 3, how I produce the key for block 3? Use the key for block 2, feed it to the cipher, the block cipher, with the key, generate yet another third key, XOR it with the third block, it gives me the cipher. And I keep going. Take a very simple message that has 2 blocks, P1 and P2. Here's my P1, here is my P2. Yeah? Now, a naive way of doing it, as I explained, I can use my encryption here. Maybe it should be here, P1. I feed it as an input to the encryption algorithm, feed the key, and produce the cipher. And I do the same for P2. Simple. One way of doing it, and you are done. But the problem, this mode of operation is deterministic. We don't want to do this. We want it to be probabilistic. Why do we want a probabilistic mode of operation? To make the cipher look random, really random. Even if you feed it the same input, it gives you a random output. That's the idea. And this way, no way somebody can do substitution attack on it, because every time it's magical. You give it the same text, every time it gives you a different cipher text. How much more confusion you can get? Plus, every block you saw what every block goes through. It goes through a series of confusion and diffusion, in case of that, 16 times. Even with this, we're still not satisfied. We still want to make it even more harder to decrypt, or to break. Yeah. So this one, no, we don't want to use this because it is deterministic. So what's a better way of doing it? Another way of doing it is this way. Here is my same P1 and P2. So the second idea is to use the block cipher, like let's say DAS or AES, as a key stream generator. So what the idea is, what I will do here, I'll take my encryption algorithm of course, it takes the key as an input, and I want to encrypt the first block, P1. In a stream cipher, if I want to encrypt something using stream cipher, what should I do? Generate a key. Generate a key for each one. That's why we call it a key stream. So for each block, it will have its own key. If I put this together, it's a key stream. It's a stream of keys for each of the blocks. Now, how I generate the key for the first block? I generate a random number, an IV. I go ahead and encrypt it. Yeah, this will produce for me. It will produce for me a stream. It will produce for me a key. Yeah, it's just basically a random number that was encrypted. It produced yet another random number, and let's call it S1. Yeah, what do I do with this S1? I go ahead, XOR it with P1, and this will produce. After this XOR will produce for me the C1. Okay, now for the second block, I need to create yet another key. Of course, I always use my key. Now, and I know the idea, it will produce a key that I will encrypt, that I will XOR with the plain text to produce C2. Now, what is the input to the second? Is basically this S1 I produced in the previous run, I feed it as an input to produce the key for the second block. Yeah? And this will produce what? S2. What I do with S2? I will feed it again, feed it here to produce S3 that I will use to XOR with P3 to produce C3. وهكذا. Okay, it's clear? So that's why we call it output. Output means I am outputting these keys. Together they form a key stream. And output feedback. Feedback because the previous output is fed back to the encryption algorithm to produce the key for the next block. So that's why we call it output feedback. That's why we call it output. Here it is. Yes. Oh, sorry, here. That's why we call it output feedback mode. Output feedback mode. Now, this is the visual way of looking at it, and this is the equation, like the algebraic equations. Let's go through them very quickly because it's very nice the way you can express this. This shows you how the power, the expressiveness or the expressive power of math, the way you can express this. It's simple, very simple to understand. So what we do here for the first block, you know, first always have special treatment, and there's no exception here. So for the first block, we generate the first key. How do we generate the first key? We generate an IV, we feed it as an input to the encryption. Whenever I say encryption, you take the key as an input. That's by definition. And then this will produce for me S1. What do I do with S1? XOR it with P1 to produce C1. Now for subsequent blocks, which is SI, I will encrypt SI minus 1, the previous key. I will encrypt the previous encrypted key, produce SI, and then all I do, I will do the XOR with PI. And this one, I do this for I greater or equal to. So only the first block has special treatment, the rest will do the same. Now for the decryption, again, exactly the same, but this time, exactly the same. You can see here, is the ID something secret? It's not secret. You send it to the recipient. When they receive it, they do exactly the same thing. Remember, the key stream has to work exactly the same for the decryption to work. You see here, it's copy-paste. The function is? Here? No, it's still encryption. Remember the key stream, the stream ciphers. What is the key idea of stream ciphers? I have a key generator on both sides. It generates some keys or key stream. And what do I do with the key stream? XOR it. These two key stream generators are identical, equal. If they are not equal, You cannot decrypt. That's why it's not, this is a trick. So don't fall into this trap. This is not decryption. I encrypt again to generate the key. Yes? So this proves to you that in stream cipher, the key stream generator is exactly the same. If it is not the same, it will not work, of course. Is clear the idea of this? It's very simple. All we're doing, we are using the block cipher as a stream cipher. Simple idea, and this is probabilistic. We feed it different text, it gives us we feed it the same text or the same plain text, a long message, it will produce each time a different cipher. Each time will give you a different cipher. Yeah? Is clear? Yes? No? Okay, so let's move on. This one is called output feedback mode, OFB. Another mode, it's called Cipher feedback mode. Cipher feedback mode. Now, this one is very, very similar to the output feedback mode. What is the difference? Can you spot the difference? We feed back the cipher text rather than the key. That's the only difference. So in here, the better name for this could have been cipher text feedback mode. That's what we're doing. So basically, in the previous mode, output feedback mode, I took the key that was used in the previous block and feed it back to the encryption to generate the key for the current mode. Now, I don't do this in this mode, in this cipher feedback mode. Instead, I feed back the cipher text that was created. And of course, for the first block, I feed the ID. First block, there is no previous cipher, so I feed the ID. That's basically the idea. Exactly the same. Again, I highlight here. You can see here you hear the key stream generator is exactly the same on both sides, the encryption and decryption. Yeah? I think it's clear, yes? Okay, the last mode that we will see is a counter mode. Counter mode. Yeah? Anybody can guess what this counter mode is? You know counter. You count 1, 2, 3, 4, 5, 6. Yeah? Okay, so what's the idea here? They are all the same idea. It's just a different way of doing it. First way, the key that you use for the previous block, you feed it to generate the key for the next block. That will be output feedback mode. The second way is you feed back the cipher itself, and it will become the cipher feedback mode. And here, you feed a counter. And this counter, it's incremented. One first counter, second counter. But of course, it should not be deterministic. Otherwise, it could be attacked. Everything should be random and probabilistic. So how do we make this counter random? Sorry? Through the random number generator. So we generate one random number, which is the IV, and then we keep incrementing the ID. Yeah? So here is how it looks, and I will explain this in more details. So in actual implementation, this is how it works. So I take a counter. What is a counter really? Counter is an IV and a counter. So let's say my block, I take my block, I'll say block size -1 in terms of bytes. Let's say for DAS, what is the size of the block? 64 in terms of bytes. How many bytes? Yes, 8 bytes. So what I do, let's say one way of doing it, you take the 7 bytes. The 7 first bytes are an IV, which is a random number, and then the 8 byte is the counter. It's a simple counter, 0, 1, 2, 3, 4, and so on. And what I do, I'll take this random number, 7 bytes of random number, one byte of the counter, and encrypt it. I encrypt this, and then once I encrypt it, I generate the, this is my S1, S2, Sn. And basically I XOR it with the plain text to generate the ciphertext. So the only difference here, I don't use it, instead of using, there is no feedback here. There's no feedback. I just use a counter. And this counter is incremented. It is that block size -1 is for the IV. And you can see this IV is the same. I don't want to create many IVs and end up with a one-time pad. Remember the one-time pad? For the whole message, I create yet another key for it, or IV for it. If it is 1 gigabyte, I have to have IV, 1 gigabyte IV. I don't want to do that. I want to create one IV, which will be 64 bits for DAS or 128 for AES, 15 bytes as a random, and last byte as a counter. Yeah? And remember, they cannot work it out because this number, I don't use it as it is. I take it through the encryption. I encrypt it. And then the output of the encryption is the one I use for XORing. Yeah? So it is very hard. It's not possible for them to reproduce this because they don't have the key. Yeah? So what do you think? What's the advantage of this mode?
There's no chain.
There's no chain. Very good. There's no chain. You see, the problem with these other modes, there is a chain. There is, which when I say chain, what do we lose when we have these dependencies? We use parallelization. We cannot make it parallel. We have to make it sequential, which means it's slower. But this one, we can make it back. We can make it parallel. Because these counters could be generated, and we can do block 1 and 2 and 3 and 4 at the same time in parallel. We just give each of those, let's say three in parallel. I can do 3 or 4 or even 5 or 10, depending on how many cores or CPUs I have, and I can do multiple blocks in parallel. Summary of the whole thing. So the electronic code book, each block is encrypted independently, but the problem, it is deterministic and could be subject to substitution attacks. Cipher block chaining, all these others are probabilistic. So the first one is cipher block chaining. What I do, I take the ciphertext of previous block, XOR it with the next block, before I encrypt. And these three output feedback and cipher feedback and counter, all of them, I'm using the block cipher as a stream cipher, which means I use the block cipher to produce the key stream. Now, the only difference between these three modes is the input. The input. In the first case, the output feedback, in the first case, the first block, I use an ID encrypted generate the key. Second block, I use the previous encrypted key, feed it to generate the second key, and so on. So the feedback is using the previous key. I feed back the previous key. Now, in the cipher feedback mode, I feed back the ciphertext itself. And in the counter mode, I don't feed back anything. Each block has its own key, has its own input as a counter. And the counter is made up of an IV, which is fixed for all of them, and a counter that is incremented for each block. And this gives me the parallel execution. And it's very fast. And there are, of course, other modes, but this is just to give you... So it is very important to choose the right mode. Why is it important? Because your choice impacts two things. Impact security and performance. Your choice will impact the security and it will impact the performance. So you need to be familiar with these modes, their advantages and disadvantages, so you can make the right choice. This ECB, straightforward but vulnerable. And the smart ones, they try to basically change the mission or change the purpose of the block cipher and change it to stream cipher, using the block cipher as a stream cipher. And as we can see, the counter mode seems to be at least for my understanding, the best one that we have seen, since it is probabilistic and at the same time it can be executed in parallel. So that is basically the block mode. We've now finished the symmetric cryptography. Inshallah, next time we will start asymmetric cryptography.